In this last alkyne video, we're going to look at a couple more reactions, and then we're going to look at some synthesis problems, okay? So the two reactions that remain that we need to still look at are these two you see before you, and they're, again, totally analogous to alkene reactions. The first is addition of halogens, okay? So we can add chlorine or bromine across the triple bond. Adding 1 mole gives us the anti-addition to produce predominantly the 1,2-dihaloalkene, like you see here, and adding a second mole gives us the tetrahaloalkane that you see as the final product. Or if we had started with just 2 moles of our halogen, we could go straight to the derivative that you see here. When we do an ozonolysis of a alkyne, we don't need a separate reduction step. Okay, so if you look at this conversion of an alkyne to an anhydride, what you see here is really a balanced equation. Now, an anhydride is a functional group that we'll take up much later in the second half of the class, but anhydrides are unstable in the presence of water, and when you treat an anhydride with water, it separates into 2 carboxylic acids. So the net result here is that the carbon-carbon triple bond is completely broken, and you end up with 2 carboxylic acid units that correspond to the original makeup of the triple bond. Okay? If you in a lot of the equations, you won't see the anhydride isolated. You'll just see this sequence here: first ozone, then water, or sometimes ozone and water together. We'll just turn the starting alkyne into the carboxylic acids. Okay, let's predict the products of each of these reactions. Some of them are in previous videos, but I think we can still remember what we did back then. Okay, so what happens when we take a terminal alkyne? Water, sulfuric acid, mercuric sulfate. This is, of course, alkyne hydration. We're going to add OH to we're going to add oxygen to one of the carbons. We're going to add 2 hydrogens to the other. Okay, because initially, remember, we produce an enol that converts to the ketone. So this is a terminal alkyne. It should be completely regioselective to put the oxygen at the more substituted carbon, and we should obtain the methyl ketone from this reaction. This next alkyne, it's a strained compound. It's an alkyne in an 8-membered ring, but it'll still do the alkyne type reactions. It'll probably do them much faster. So when this is treated with 2 moles of HCl, what we're going to see is that one of the carbons gets 2 hydrogens, one of the carbons gets 2 chlorines. It doesn't matter which is which because this is a perfectly symmetrical molecule, and we end up with 1,1-dichlorocyclooctane. Okay, in this reaction, in this next reaction, similar strained alkyne is treated with ozone followed by water, and this is just going to, as before, break the carbon-carbon bond that originally was a triple bond, and we're going to end up producing the dicarboxylic acid. Since it was a cyclic compound, that means that we have one molecule that has 2 carboxylic acid groups in it. All right, here we're going to treat it with chlorine, 1 mole, and then treat it with bromine. What we're going to find is that since it starts out with a fluorine, it's the product is going to have 3 different halogens in it. First, we're going to add chlorine and add 1 chlorine to 1 carbon, 1 carbon to the other, and get an alkene. Then we're going to add bromine to the resulting alkene and produce that compound. It's probably going to be also 2 anti-additions, so the real product that we would get would be this product that you see right here. So the first step is going to give us the anti-addition product to the, okay, and the second step is going to add bromine to the alkene that we have right there. All right, here's a synthesis problem. Outline all reagents that are needed to perform the following interconversion. All right, so there's a couple of hints here. The product has a longer carbon chain than the starting material. That means you're going to have to use the only carbon-carbon bond-forming reaction that's been introduced in this class to date, and that's the alkylation of acetylenes. Okay? We don't know of any reactions that directly add carbons to an alkene group, so again, we can't just take the starting material and deprotonate it. It's not acidic enough. We also know that our product alkene is of the cis geometry. So all of these things are telling us that we have to turn the alkene into an alkyne and then ultimately reduce the alkyne to the cis alkene. Remember, we don't know any other reactions other than alkyne reduction that is going to generate this system right here, an alkene of the cis geometry. All right. So our last step is going to be the Lindlar catalyst reduction of the alkyne shown here. Okay, adding hydrogen in Lindlar's catalyst is going to put in 2 hydrogens. Remember, the 2 hydrogens add Synth, so therefore the hydrogens are going to be cis. That means the other 2 groups also have to be cis. Okay. Once we look at this compound, of course, we see that the bond that we have here between the ethyl group and the alkyne is going to ideally be installed using this alkyne alkylation. Okay, so in the second to last step, we're going to take this compound, this acetylene right here, remove the proton that's right there, and alkylate it, and that's going to turn the hydrogen that we originally started with right here into an ethyl group. Okay. All right, so that's our second to last step. Remember that our ultimate starting material is the alkene that totally corresponds to this alkyne right there. Okay, so we need to think about how do we turn the alkene into an alkyne. Remember, we earlier showed a 2-step protocol for doing that. You're going to add halogen across the alkene and then do a double E2 reaction to turn the dihalide into the dialkyne. All right, so when we assemble this multi-step synthesis together, it's ultimately a 4-step synthesis. We're going to add halogen to the alkene. Okay, our dihalide is turned into the alkyne through a double E2. We do this alkylation, deprotonation, followed by SN2 reaction to produce the compound with an ethyl and a cyclohexyl group attached to the acetylene. And then in the final step, we do the Lindlar reduction to produce the alkene of the cis geometry. Okay. All right, let's do another synthesis problem, and this is the last slide. We're going to design a synthesis of the meso diastereomer of 3,4-dibromohexane using acetylene as a source for every single carbon atom in this compound. And then we're going to see how we could adjust our synthesis to produce the chiral or DL diastereomer from this reaction. Recognize that this starting material has 2 carbons, acetylene. Our product has 6 carbons. Therefore, it looks like we're going to take 3 different acetylene units and incorporate them into this final product right here. Okay? And that's exactly what we're going to do. All right, so if we're going to make meso, that means we need to do an anti-addition to this compound right here. So we need the transalkene to make miso. And if you don't remember what miso is, let's see. We can't really tell it's miso from that conformation. That's just the way people normally draw acyclic molecules. All right, so we have to turn it into a conformation where things are lined up. And when you look at it that way, you see, of course, that this is, in fact, miso. There's our imaginary plane of symmetry right there. Okay, bromine, hydrogen. Okay. The only reaction that we've had to date that makes an alkene of the trans geometry is, of course, the lithium and ammonia reduction, or sodium ammonia reduction of an alkyne. So using that alkyne as a precursor, we would get the alkene that you see here. We're going to have to basically alkylate acetylene itself 2 times. So we're going to take acetylene, treat it with sodium amide, then ethyl bromide. Okay, that's going to turn acetylene into a terminal alkyne. Okay, so after step 1, we're going to have butyne, and we're going to repeat the process, and after step 2, we're going to have the product that we see there. Okay, so this is our sequence. Oh, what else do we need to do? Okay, so it says to make everything from acetylene. What about, that must mean that I'm going to have to make ethyl bromide from acetylene. Okay, all right, so this compound doesn't qualify or it's not satisfying our directions in the problem, just pulling this compound out of thin air, so we have to design a synthesis of this. I'm going to say let's take hydrogen and Lindlar's catalyst, reduce that to the alkene, and then take the alkene and treat it with HBr, and that should give us the ethyl bromide. All right, the last aspect of this synthesis is how do we generate the diastereomer? Well, remember that when you're talking about stereospecific reactions that do either syn or anti-addition, that the compounds you get from the E or the Z alkene are diastereomers. So this tells us that instead of using the trans compound in the last step, we need to use the cis compound in the last step. And so we would change this second to last step. Instead of doing the trans-selective reduction, we do the cis-selective reduction using hydrogen and Lindlar's catalyst. Okay? From that perspective, it looks like that doesn't really look like that product, right? All right, so we have to rotate this thing around that axis there, and that gives us the same product that we have depicted right there. Okay, so that's how we would adjust the synthesis for making the chiral compound instead of the miso compound. Okay, so this is the last slide of the alkyne chapter, so I'm going to end that